Remember last week we were talking about what were we talking about last week? I don't even remember anymore.
The graphing stuff.
Right. Okay, let me do it in different colors. So we were saying, let's say we had f of x is equal to, and then we have a, and we have b x minus c and plus d, right? So we focused last week on just C and D, right? So basically translations, moving the graph either left or right or up and down, right? So that was from last week. Okay. Now, what we're gonna do this week is we're gonna focus on this part right here, which is the A and the B part. Well, not so much the B, and the reason why is because it can get a little confusing. A and B kind of go together. So whatever happens with A is kind of the opposite of what's going to happen with B. So kind of go through it, but not really. Like it's not really, don't go over it too much. But A and B deal with the dilation and reflection of the graph, okay? So does anybody remember what a dilation means?
It gets smaller or bigger.
Right, so it actually changes the shape of the graph, right? It could either get smaller or bigger depending on the dilation. And what about the reflection?
It's reflected across a certain point.
Not necessarily a certain point, but maybe a certain line, right? So if we have our graph here, X and Y, it's probably either going to be reflected across the x-axis, or it could be reflected across the y-axis or whatnot. So that's what we're going to focus on, okay? So let's start by saying, okay, if A is negative, then we reflect across X. Across x-axis. So let's think about our absolute value graph that looks like this, right? If it reflects across the x-axis, what would happen to it?
Become a positive, right?
No, not necessarily. We're saying that we're reflecting across the x-axis. So what is that going to do to the graph?
It flips it.
It flips it which way? Down or? So it should look like this, right?
Yeah.
So what's going to happen is that we're reflecting, this is our parent function. If we reflect it across the x-axis, it's going to point downwards like this. Okay, so that's what it means when we're talking about A is negative. That means that we're going to reflect across the x-axis. Now, if A is greater than 1, then we have a vertical stretch. Now, if A is greater than 0, but less than 1, we have a vertical compress, or however you want to say it. Okay, so if something is between 0 and 1, what does that mean?
I don't remember that, sir.
So something is between 0 and 1.
I don't know.
So think about it in a number line. Let's say we have a number line.
Wouldn't it be a decimal?
Yeah, right. So let's say a 0 and a 1. So something is between 0 and 1. We're talking about that space in between. So it's either a decimal, or another way of thinking about it is it's a fraction. Okay. So we're basically having a fraction because it's got to be between 0 and 1. So it can't be a whole number, but it can't be 0 either, right? So it has to be a decimal or a fraction between 0 and 1. Okay. So that's what we got so far for A. Okay. Okay, so let's think about here. Give me a second here. Okay, guys. So let's think about what these things mean, okay? So when I'm talking about a vertical stretch, right? So let's pretend we had a rubber band, right? So if we had a rubber band and we stretched it vertically, right? So let's say that we pulled it apart, right? We stretched it vertically like that. So the rubber band should look something like this. If we stretched it apart, it should look like this, right? Does that make sense?
Yep.
So if we're stretching something vertically, okay, what is happening to the sides? So let's just say this is the original rubber band, and then we stretched it vertically. So what happens first to the sides?
They grow.
They what?
Grow.
Well, they grow, sure, but what did you say, Lindsay?
So they go in.
So they're going in. That's right. So they do get bigger. That's true. But more importantly, they're going in. All right. And then the rest of it is getting a little bit bigger. Okay. So that's sort of the same thing that happens when we're talking about a graph, and then we'll see it in a little bit. So now let's do the opposite. Now let's say that we're going to take that same thing and we're going to compress it. In other words, we're going to take it like this and then we're going to put it together in a way, right? So it should end up looking something like this, right? So now with this, what happened? Well, what was the opposite thing that happened here?
The sides expanded.
The sides expanded, yes. So it looks a little bit more like this. And the thing just got kind of shorter, just in general, okay? So when we're talking about a vertical stretch and a vertical compress, that's exactly what we mean, okay? So now, let's think about and I'm gonna go through B, but again, like I don't really focus too much on the B part because it kind of becomes a little bit irrelevant, I guess, you know? So let's say we have B, okay? And B is negative. So we are going to have a reflection over Y, over the Y-axis, okay? Now think about that. If we're reflecting something over the Y-axis, and again, we have our parent function.
Really?
Okay.
Are we leaving at 3? Because we have to go.
Oh, I'm gonna ask my mom if
She doesn't know.
So if it reflects over the Y-axis,
closed.
So what would happen to the graph? Okay, so if we're reflecting over X, it looks like this, right? But if we're reflecting over Y, what's happening?
It stays the same.
It would stay the same because if we reflect it over Y, if you notice, it looks exactly the same, right? Nothing changes, okay? And the reason why is because our graph is symmetrical, okay? So if we were to just spin it around, it just looks the same. So that's why we're reflecting over Y, but in reality, I mean, we're not really doing much. And that would make sense, right? Because let's say if B is negative and it's inside the absolute value, eventually what's going to happen to it? So if B is negative and it's inside the absolute value, eventually what will happen?
I don't know.
Well, I mean, it would turn positive, right?
I was gonna say it'll end up becoming positive.
It doesn't, yeah, because it doesn't matter what happens in there because of the absolute values, it's going to end up turning positive either way, right? So it makes sense that the graph would stay the same if it reflected over the y-axis, okay?
C.
And when I do that, that's kind of a, in England, that's kind of an insulting symbol. So good thing we're not in England, right?
Why?
I don't know. It's just I'm not really gonna explain it, but it's sort of like it's kind of like giving someone the middle finger in England when you show the back of your hand like that. I don't know why. Just kind of a weird thing. But anyways, so B, if B is greater than 1, we're gonna have a horizontal compress. And if B is between 0 and 1, meaning it's a fraction, we're gonna have a horizontal stretch. I spell horizontal wrong over here. Okay. So,
Wait, sir.
yeah.
I thought if B was greater than 1, it'd be a horizontal stretch.
So,
Or is it not the same as the vertical one?
so that's, yeah, it's not the same as a vertical one. So that's a good question. But here, I'm gonna go over it because this is what's, I guess, what's kind of funny, right? So this is what I mean by the things kind of go together, okay? So, like you mentioned, right? B, if A, and let me just take these off, but say, if A is greater than 1, then you would have a vertical stretch, okay? So it's not necessarily the same thing, right?
I think I get it now.
Yeah, but let's think about it again in terms of our rubber band, right? So if we have this rubber band and we're gonna horizontally compress it. So if we horizontally compress it, that means that from the sides, we're gonna go like this, right? So that should end up looking like this. But if you notice, what is that similar to? Or actually not similar, but what is it the same as?
A vertical stretch?
Exactly, right? So they mean the exact same thing, right? When we're talking about a vertical stretch and a horizontal compress, they're exactly the same thing, okay? What's happening is that our sides are getting smaller, but our rubber band is getting bigger. So the same thing happens. And let's talk about, for example, a horizontal stretch. So if we were to stretch this horizontally, so we're taking it and we're stretching it like this, it would end up looking like this, which is also the same thing as a vertical compress. Okay, so both of those things are exactly the same thing, and that's why, you know, I kind of don't focus too much on the B part because they mean exactly the same thing. Okay. All right, so almost done here. Let me just. Okay. So let's say we're gonna have say these are our graphs right here. So f of x All right, so let's start with our parent function, right? And our parent function basically always looks like this. So that's our parent function, okay? Now, for f of x is equal to 2 and then the absolute value of x, what kind of transformation do we have there?
Like
Wait, what?
infinity?
No, I'm talking about the red graph. The f of x is equal to 2, absolute value of x. What kind of transformation is that? So if this is our a, right? We're talking about our a. So if a is greater than 1, what kind of transformation do we have there?
Wait, the what?
Since our a is greater than 1, right? Because we're looking at the first graph, f of x is equal to 2, and then the absolute value of x.
So that'd be a. I don't remember.
That would be a vertical stretch.
Yeah, but it reflect. Wouldn't it be a reflect? A reflection?
No, not in this case. It's only if we have a negative number, okay? So the 2 tells us that we're going to stretch. So the way that we're going to graph this is just say, okay, 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6, and so on, okay? And 4 times 2 is 8. Same thing on the other side, -1 and 2, -2 and 4, -3 and 6. Okay. So if you notice, we stretched it, basically saying that we pushed it a little bit inward.
By 2, right?
Yes, exactly, by 2. So we have our vertical stretch. Okay, now let's look at our yellow graph. F of x is equal to 1/2 absolute value of x. So what kind of transformation would we have there?
beats me.
So that would be a vertical compress, okay? And the way that we're gonna graph this is again saying, okay, 1 times 1/2 is 1/2. 2 times 1/2 is 1. I'm gonna say 4 and 1/2, that's 2. 6 and 1/2 is 3, and so on, right? So 1, 2, and then 6 and 3. Okay. So as you can see, we compressed the graph, basically saying that it got a little bit shorter and the sides kind of got longer, right? So we pushed it a little bit outward. Okay. And our last one right there we have is a negative absolute value of x. So what's going to happen to that one?
Is that the one where it reflects?
Exactly, right? So we're just going to take the parent function, and it's going to be facing downward.
Over the x-axis, right?
Yeah, over the x.
Oh yeah, and then if it were b that or x that were negative, it would be over the y-axis.
Exactly, but if it's over the y-axis, nothing changes. It looks exactly the same.
Yeah.
Okay. So let's see. Okay. So again, this right here, let's just say that this was our parent function. Now, when we stretch the graph, it should look like this. When we compress the graph, it should look a little more like this. And when we reflect the graph, it should go downwards like that. Now, when we do a vertical stretch or a horizontal compress, do our domain and range, do any of those things change?
I may be wrong, but I want to say yes.
You want to say yes?
Because it moves like a coin. I don't understand this. This is 101.
So let's think about our domain. Our domain would be all real numbers, right? Now, if I stretch the graph or compress it, it doesn't actually move from 0, right? It stays there. And we still have our arrows. So does our domain change?
Oh no.
What about our range? Our range should be y is greater than or equal to 0. Does it change at all?
No. There's a B.
Yeah, so nothing really changes, okay? The x and the y-intercept are the same, and then our minimum is still 0. All right? But the opposite thing, right? So let me ask you this now. If we're reflecting across the x-axis, would our domain, range, and all that other stuff change?
I think
You said if we're reflecting over the x-axis?
Right, if we're reflecting. So now let's think about, and let me just take these out. Now let's just think about the red one is a parent function, and then we reflected it over the x-axis.
So yeah.
Okay, so let's see. Our domain, it'd still be the same, right? That doesn't really change because the arrows just tell us that it's going to hit every x value. So the domain is still all real numbers. But the range does change. What is the range now?
It's now everything not greater than less than.
Right, so it's everything less than 0. So our parent function is our real number, so that stays the same. And our range would be y is greater than or equal to 0. But, and let me do this in a different color just so we don't get confused, but our domain for our reflected graph would be all real numbers as well, but our range changes to y is less than 0. Now our x and our y-intercept, those don't change, we're still at 0. But our minimum isn't 0 anymore, right? Well, it still is 0, but it's not a minimum anymore. What would it be called now?
Wait, what?
So the minimum of our parent function is 0, right? So the minimum would be 0. But now when we reflect it, our minimum actually turns into a maximum because we're talking about the maximum the graph is going to reach. So we're still at 0, but now our minimum has turned into a maximum. Does that make sense? Okay, so just like last week,